Okay, this is one of those that you either remember the formula or you don't. If you remember it, you're all set. You can factor it. If you don't, you can't. So this is a difference of cubes, remember. So it's going to be perfect cube of x, and this is a perfect cube of 2. So this is going to be x and a 2. And is this plus or minus?
Minus.
It's minus. Remember, if there's a negative in between those, it goes in the middle of that first one. There's only one negative in the formula, so the rest of these are going to be positive, and this is going to be x squared. This is going to end with a 4, and it's going to be positive. And how do I get that middle term? You just multiply them together. So this is going to be plus 2x. Okay? So that's what we get when we factor that. And then the next question on B and C, it says, what would the common denominator for the following problems be? So if we were going to combine these, let's think about how we'd put these together. So this one has a factor of x plus 3. This one has a factor of x minus 1. And that has a factor of x minus 1 quantity squared. So what does this one over here need in order to get a common denominator? Okay, it needs an x minus 1, x minus 1 squared, right? What does this one need? Okay, it needs another x minus 1, so I'd have to multiply the top by x minus 1 squared. It needs another x minus 1, and it needs an x plus 3, right? So I'd have to multiply the top and bottom by x plus 3, and the top and bottom by another x minus 1. And what does this one need? It just needs an x plus 3. Okay, so I multiply the top and bottom by x plus 3. So that's going to give me a denominator of x minus 1 quantity squared and an x plus 3, right? And then I'd have x minus 1 quantity squared, and then plus x plus 3 times x minus 1, and then plus x plus 3, right? Okay, now it just said what's the common denominator, and that's the common denominator, right? Any questions there? You did this in 1010. We kind of reviewed how to do this in this class. Sure there aren't any questions, because this is critical to understanding what we're doing today. Okay, let's do the next one. I want to get the common denominator for this addition problem. What does this one need? Needs an x minus 1 quantity squared, which means I need to multiply the top and the bottom by x minus 1 quantity squared. And what does this one need? This one needs an x plus 3. Okay, now I'm not going to bother to, well, let's go ahead and do it. The denominator is x minus 1 quantity squared and x plus 3. And then the numerator would be x minus 1 quantity squared and then x plus 3. Now, I don't do this very often, but Tylin, do you want to say that again? What is that? They are the exact same. Those denominators are exactly the same. Look at them. Now what I want you to look at is look at the original problem. That had a denominator of x plus 3. That had a denominator of x minus 1. And this had a denominator of x minus 1 quantity squared. How many terms was I adding together here? 3. How many terms was I adding together here? Just 2. Okay, now you really couldn't tell whether or not that denominator, this one right here, this middle one, I mean, whether it was there or not really didn't impact what the common denominator was, did it? Here's one that had 3, here's one that had 2, and yet they have the same denominator. You with me there? Okay, so I need you to keep track of that, because that's going to help make sense of this method in just a second. Might take a while before we get there, but hopefully it'll make sense. Okay. Let's see. Let's go ahead and add these together. Let's see. This would be x squared minus 2x plus 1. X squared minus 2x plus 1. And then this middle term would be x squared. Let's see. I'd have a plus 2x and a minus 3. And then I'd have an x plus 3. Is that right? X minus 1 quantity squared, x plus 3. And let's see, where can I write this answer? Let's collect the like terms. I've got 2x squareds, done with those. Let's see, I've got a minus 2x and a 2x. Those go away. So I'm left with a plus x and then I'm left with a positive 4. Now, if we were into simplifying here, we'd try and factor the numerator. Does the numerator factor? Use the little trinomial grouping technique. Multiply 2 and 4 together, you get 8. Are there any numbers that multiply to be positive 8 that combine to be positive 1? No, that means it's prime. Okay, so we'd be done right there. Okay, so you're really familiar with, although this wasn't a fun problem, you're familiar with how to take fractions and combine them together. We're used to doing what we call simplifying. I mean, usually this is going to be a better answer than leaving that as 3 separate ones. Okay, well today we're going to learn how to do the opposite of that. Okay, so this is called partial fraction decomposition. Partial fraction decomposition. Okay, what does the word decompose mean? Okay, it means break down. So if we say partial fraction decomposition, here's what we really mean. Now there's a reason why they didn't call it this, because it's a big long sentence. It's just easier to say those 3 words. We're going to break down a fraction into its parts. The word partial, root word is part. So we're going to take a fraction and we're going to break it down into its parts. So we're essentially going to do the exact opposite of what we did here. We're going to take a fraction that looks something like this, and we're going to break it into the, listen carefully, into the 3 or maybe just the 2 parts that it came from. So into the 3 or the 2 parts that it came from. Okay, so that's partial fraction decomposition. Okay, there are several methods for this. There is a shortcut for the fairly easy ones, but there are ones that we're going to run into. There's no shortcut for them. You need to understand how to do these the long way. Okay, so I'm going to show you several different methods to do these. One point that we want to make is we can only decompose fractions if they are proper fractions. Okay? If it happens to be an improper fraction, remember that's where the degree of the numerator is bigger than the degree of the denominator. You can do that, but you have to do long division first. Okay? And I'm going to do one problem like that, but we won't finish it and actually do the decomposition. If you run into something like that, that technique is used when you get into second semester calculus. Okay? You don't have to worry about it in 1050. Okay? So this looks like a very long list of things that we need to do to decompose these. But again, like most things, once you understand it, you kind of tick that list off just kind of automatically. It's not like you memorize all 5 of these steps. So here's the first step to partial fraction decomposition. We want to factor the denominator completely. Take whatever the denominator is and break it down as far as you can. Factor it completely. So you're going to get what we call linear factors, and those are really nice. And then we also sometimes will get irreducible quadratics. Irreducible quadratics. Quadratic factors that don't factor. Okay? You can't break them down into linear factors. They'd be like prime polynomials, so to speak. Okay? So then we're going to break the fraction into the parts it may have come from. And this is important. Parts it may have come from. Remember that example up at the top in the starter question. We had 2 answers that had the same common denominator, but they came from completely different fraction problems. One had 3 parts to it, and the other one only had 2. So we want to break it down into the parts that it may have come from based on the factors in the denominator. So we're going to write down 1 part for each factor in the denominator and 1 part for each of its repeated factors if necessary. Okay, now this part right here, whoops, let me star that. That's the part that's important. People typically forget that, and I'll show you where that comes in. The next thing is we're going to place undetermined coefficients. This is what we call them. Undetermined coefficients in the numerator of each one of those parts. So if there are 5 parts, we might have to put an undetermined coefficient in each one of those. And this is the key thing that you want to remember. Something else people forget. The degree of the numerator is 1 degree less than the factor in the denominator. It's not the degree of the denominator that matters. It's the degree of the factor in the denominator that makes the difference. Okay? Then generally speaking, the best way to solve these is clear the fractions from that equation, okay, using an appropriate method. Okay? We can call these convenient numbers. I like to call them, Miss Cavan calls them sweet numbers. I like to call them convenient zeros, and you'll see why. We'll solve using a system of equations. And there was actually a guy named Oliver Heaviside. How would you like that name? That was his real name, Oliver Heaviside. It's called the Oliver Heaviside cover-up method. Okay? You can Google him when you get out of here. Pretty interesting guy. Okay? Convenient numbers or convenient zeros. And you'll see why I like to call them convenient zeros in a second. Okay? And then the last thing is, don't forget this. You want to go back and you want to write the original factor as the sum of its parts. We're taking a fraction, we're breaking it into a bunch of different parts, and then we're going to rewrite the original fraction that way. We're going to say, hey, you know this original fraction we were dealing with? Here are the fractions that it came from. Here are the parts that we decomposed it into. Okay? So we're going to start with something very easy. It's not partial fraction decomposition. It's a problem that you already know how to do. It says, write as the sum of a polynomial and a proper rational expression. That's just code for do long division. Okay? So if I do long division on this problem right here, I'd write x squared minus 1 outside the box, and then I'd write 3x cubed. I write plus x squared. What do I write next? 0x to save a place for that, and then I write the 5. Again, I just look at the leading term on each one of these. What do I multiply x squared by to make it a 3x cubed? A 3x. So that's going to make this a 3x cubed. That's going to make this a minus, whoops, put this in the right place, minus 3x. Then I go through and I subtract, or I change the signs. So I end up with, let's see, this x squared can come down. That's going to be a 3x, and that's going to be a plus 5. Any questions? What do I multiply x squared by to make it x squared? A 1. So I multiply here, I get x squared, I get minus 1. Then I go through and I subtract, or in other words, I change the signs. So those go away. This is going to be a 3x here, and this is going to be a 6. Now, can I multiply x squared by something to make it a 3x? Not a regular old polynomial term, okay? So we're done right here. This is, anybody remember the name for this? Quotient. This is the remainder, and this is the divisor. This is what we were dividing by. So the answer to this is the quotient plus the remainder divided by the divisor. Okay, now take a look at the instructions. The instructions said, write this as a sum of a polynomial and a proper rational expression. Is that a polynomial right here? Yes. And is that a proper rational expression? Yes. The degree of the numerator is less than the degree of the denominator, so we're in good shape there. Okay? Any questions? Okay, let's do some partial fraction decomposition then. There's the fraction. We want to decompose it into its parts. We want to break it down into the parts that it came from. So this is like the answer to a fraction addition problem. And we want to break it down and we want to say, what problem did this come from? Okay, now, are you going to use this all the time? Probably not. Will you use this if you get into calculus? Absolutely. Okay? So that's why they teach you how to do this. This would be overwhelming to learn how to do this and how to do the calculus that you have to do with these types of problems if they did it all at once. So that's why they introduced this in 1050. So, first step, what was the first thing that it said to do? Factor the denominator, okay? So we're going to take the denominator and we're going to factor that. Luckily, this factors easily. We're looking for two numbers that multiply to be positive 6 and combine to be negative 5. Careful here, let's make sure we get it right. Negative 2 and negative 3. Now, nothing is more frustrating than making a silly mistake like this and barking up the wrong tree and getting the whole thing wrong. So please double check and make sure. Did we get the right factors? Yes.
Was there supposed to that also be factored into x minus 6x plus 1?
No.
Because they'll times be negative 6.
Oh, okay. It's okay. I'm not
Okay. Say that again. Just kidding.
retarded.
Good? Oh, did it disappear? Good there? Okay. Once we have it factored, then it says, what's the second step? Break the fractions into its parts. Now, These two factors wouldn't be in the denominators or of the answer if they weren't in the denominators of the parts. So we're going to take this, and one of the parts must have had an x minus 3 in it, and the other one must have had an x minus 2 in it. With me there? Those factors wouldn't be in the answer if they weren't in the parts. So we'll do one for each part. The next thing is, what's that fancy phrase there? It's in bold. Undetermined coefficients. That's a fancy way of saying there must have been a number up here and here. Let's figure out what it was. So this is degree 1 in the denominator. The denominator is degree 1. The numerator is always, I'll say this several times, make sure you get it. The numerator is always 1 degree less than the factor in the denominator. What degree is this factor? Degree 1. What's 1 less than 1? 0. So the numerator has to be degree 0. If it's degree 0, it doesn't have an x. It's just a plain old number. So by convention, we usually use a capital letter for that. And we start at the beginning of the alphabet. Remember, letters at the beginning of the alphabet represent constants. Letters at the end of the alphabet represent variables. So what degree is this factor? 1. What degree would the numerator be then? 0. So we're going to use b. They're the undetermined coefficients. So we just start with a, then b, then c, and so forth. Okay, I only need 2 of them. So I only have to find, to finish this off, I only have to find out what a is and what b is. Okay? So here's the next step. I'm going to change colors. It says, if you look at your sheet, clear the fraction from the equation. Now take a good look at this right here. Oops. This is an equation, right? Okay, do you like working with fractions and equations? Nope. So what do we do to clear the fractions? Multiply it by the denominators, right? So if I were to multiply by x minus 3 and x minus 2, what happens here? They cancel. So I just get an x plus a 1, right? What happens when I multiply here with the term with the a in it?
It's a with that.
Okay. It's the a, and we're left with an x minus 2. And the x minus 2 cancels here, so we're left with a b and an x minus 3. You with me there? Okay. Now, we're going to use the method of convenient zeros. Okay, look at this right here. What are the zeros in the denominator? 3 and 2. Okay, so I'm going to plug in x equals 3 and I'm going to plug in x equals 2.
Why?
Watch what happens. Okay, this is why it's called convenient zeros. This is just an equation. Okay, if this was a true equation, this should be a true equation. If I plug a number in for x, it should still be a true equation, right? So watch what happens when I plug in a 3. I get 3 plus 1. I get a times 3 minus 2. And I get b times 3 minus 3.
Oh my gosh! It works.
I am glad we have somebody so animated as Thailand. Okay. What happens here? It turns into a 0. Do you see why we call this a convenient zero? Not only by choosing x the right way, not only did I get rid of the variable x, I made it a number, I get rid of the b also. B gets multiplied by 0, that's completely gone, right? So this is 4 equals a. Got one of them. See how convenient a choice that is? Okay, let me say this again. The only thing special about that is it makes it 0. You could do that with any number you want, but it's not going to turn that factor right here into a 0. That's why it's such a convenient number. That's why it's a convenient 0. What happens when we plug in a 2? I get 2 plus 1, 2 minus 2, 2 minus 3. This goes away. This is a 3. And this is a negative 1 times b, so this is a negative b, so that means b is equal to negative 3. Okay, now, I'm going to do this a couple different ways, but let me come up here and finish this problem off. What we're saying here is, I know what A and B are now. So if you look at this original problem right here, I can tell you the parts that it came from. It came from, what's A again? Came from 4 over x minus 3 plus, what's B? Negative 3 over x minus 2. This is the problem that it came from. Now, could you slide that negative out front and say this was the problem? You could. Okay, everybody watch, please. This right here is the answer. That's it. What we're saying here is, if you started out with this problem, it came from these parts. And all I can tell you right now is, this problem right here, these parts would be easier to work with in calculus than this would. So if you go, let's see, 1 year past where you are right now, 1060, 1210, if you took 1220, you'd see problems like this where you would use this technique. Okay? Any questions? And you're going to see them on the test, so get over it. Okay, good there?
Wait, why are you doing one?
Because I'm going to show you the other method. Okay?
Why didn't you make a room?
Okay, the other method is to do this. Everybody watch, please. This side is x plus 1. This side is ax minus 2a plus bx minus 3b. What I've done here is I've just distributed through. Now, if this is truly an equation, this side should equal this side. Now watch very carefully. We don't do this very often. This side is x plus 1. This side is ax plus bx. Well, that's an x term. Those are like terms, and it would be, here's how I like to write it. Start a set of parentheses. It's a plus b, x. Now, I've taken care of the a and ax and the bx. Let's look at what's left. You're left with a minus 2a minus 3b. Now, I like putting those in parentheses. Whoops, that's a 2. I like putting those in parentheses. This is the x term right there. And this is the number at the end. So that blue highlighting there, that's the constant. And the yellow highlighting, that's the coefficient in front of x. Now, this technique is called solving using a system of equations. So, if these two sides are equal, they both just have two terms. This x term had better equal that x term. Well, what's the number in front of the x? A 1. So 1 had better equal a plus b. And this number right here, 1, had better equal negative 2a minus 3b. And then you solve this like you would any other system of equations. Okay, I'm going to solve this one using elimination. I'm going to multiply this one by 2. So that's going to give me 2, 2a, 2b. And when I put those together, I get a 3 here, and I get a minus b. So what does that mean? B is equal to negative 3. Now, once I know what b is, then I can come up here and I can plug it in. And I get 1 equals a minus 3. So if I move the 3 to the other side, I get a equals 4.
Oh my gosh,
Same answer. Okay, which method's easier? System of equations or convenient zeros? Convenient zeros is easier, but you will run into problems where you can't use all the convenient zeros. So you have to rely on a system of equations. And what it amounts to is, write a polynomial on this side, it's whatever the top is over here, and distribute through and write the polynomial there and collect like terms, okay? And then you're just setting the terms equal to each other, or maybe the coefficients would be a better way to say it. That one has to equal a plus b. That one has to be equal to negative 2a minus 3b. Any questions there? Okay, would you like to see what Mr. Heaviside came up with?
Yeah.
Okay. Okay, so here's how you do it. I'm going to write this blue thing again. X plus 1 x minus 3, x minus 2 equals a x minus 3 plus b x minus 2. Everybody with me? Just rewrote that. You ready? Okay. What's the 0 underneath the a? It'd be a 3. You with me? Cross that out. Cross it out here. Plug a 3 into this. So if I plug a 3 in here, I get 3 plus 1. If I plug a 3 in here, I get 3 minus 2. What is that?
4 over 1, 4. A equals 4.
Okay, you really need to calm down. I'm not even that excited. So that's what A is. So what Oliver Heaviside figured out is, you know what? You can just plug in whatever the 0 is. Cover this one up. You can barely see it, right? Cover that factor up in this part over here on the other side and just plug in that number. You get a 4 on the top, you get a 1 on the bottom, so the answer is a 4. So if I'm going to do the other one, if I'm going to figure out what B is, what factor do I need to cover up? I need to cover up the x minus 2, and what number do I need to plug in? I need to plug in a 2. So if I plug in a 2, I get a 2 plus 1 on the top. I get a 2 minus 3 on the bottom, so I get a 3 over negative 1, and that is negative 3, and there it is right there. Okay? So that is the easiest one. Okay? Can somebody tell me why it works that way?
Because it's so cool. Does that work every single time?
It only works for, get this, non-repeating linear factors. It only works for the really easy ones. So what that means is these two are different factors and they don't repeat.
So,
Non-repeating linear factors. If it repeats or they're non-linear, they're an irreducible quadratic, that technique does not work. Okay? So you're stuck doing one of these other two. Okay? And I guarantee you there's going to be one of those other two on the test. Okay? And there's also going to be one where it's got some repeating linear factors or maybe some quadratic factors, so the Heaviside method won't work. Can anybody tell me why the Heaviside method works? It's just a shortcut on this one right here. Look what we did every time. Look what was left. This was a 1. If you divide both sides by 1, you get 4 over 1. All they've done is move this factor of 3 minus 2. See that right there? It's just on the bottom now. It's a little easier to see right here. See the B? We would divide by 2 minus 3. There's the 2 minus 3 on the bottom of the 2 plus 1. It's just it's a tiny modification of this technique right here of convenient zeros. Okay? Any questions? You need to know all three techniques. That cover-up method works really slick. The convenient zeros is a very, very useful technique, even for the ones that are more complicated. And you can't get around this system of equations idea, the fact that you're going to write two polynomials on each side and then set the coefficients equal to each other. Okay, we're good? Okay, let's run through and do this one. I'm going to do this one using convenient zeros, and I'll show you why. First thing we always do is factor the denominator.
We're just doing convenient zeros on this.
I'm only going to do convenient zeros here because in the long run, I think that should be your mainstay. I really wouldn't use that shortcut, the Heaviside method, very much at all. I need the right factors. -4 and +3, right? Next thing I do is I break this down into its parts. So one part for each factor in the denominator, including its repeats if necessary. Each one of these only appears once. I don't have any quantity squared or quantity cubed or anything. So this is kind of like I did the last one. Zach?
so if it did have like an x minus 4 squared, you'd have to write 2 x minus 4s.
You would, and I think there's one of those coming up. If not, I'll be sure to do one. There's one right there. There's number 25. Okay.
My heavens.
Okay. What's the degree of the factor in the denominator? 1, so the numerator's degree 0, so it's a plain old number. Degree 1, so the numerator's degree 0. The next thing we're going to do is we're going to take this and we're going to clear the fractions. So I'm going to multiply by x minus 4 and x plus 3. That means this side is just going to be an x, and this side is going to be, well, the a is going to be multiplied by whatever the other factor was, right? So this is going to be a and x plus 3, and this is going to be b and x minus 4. Okay, this is going to be your mainstay technique. This is what you're going to use most of the time. If there are any convenient zeros, plug them in first. So do I have a convenient number, a convenient zero to plug in? Okay, let's do 4 first. Okay, if I plug in a 4, here's what I get. I get 4 equals a times 4 plus 3. What does this turn into? Okay, I'll write it this time. Eventually, I'm just going to stop writing it. That turns into a 0, correct? 4, 7, 7a equals 4. A equals, 4 sevenths. Not the nicest number in the world, but we can deal with that.
Wait, why'd you? Oh, okay.
We love listening to you think out loud. Okay, do I have any more convenient zeros? Plug in convenient zeros until you run out. Plug in convenient zeros until you run out. So we're going to plug in a negative 3. That's going to make this side negative 3 because it's just an x. This is going to be a times negative 3 plus 3. That does exactly what we expect. That's going to make this go away. And then this is going to be b negative 3 minus 4. So here's what I get. I get negative 3. I get negative 7b. So that means I know what b equals. b is equal to 3 sevenths. So I know what those are. Chill out. Rhyminy. Okay. What a lot of people will do is they'll just, wipe their brow off, think, my gosh, I've done a bunch of work already. I've got to be done. I know what a and b are. We're not done because the whole idea of this was to break that fraction into its parts. So its parts could be written like this. Now, I don't mind you writing it like this. If there's one of these on the test, go ahead and do it this way. So this would be 4 sevenths over x minus 4 plus 3 sevenths over x plus 3. That's totally fine with me. Now, if you didn't like that, if that bothered you, or you looked in the back of the book or somebody said, hey, that's not quite right, you can clean that up just a little bit. Okay? Slide the 4 sevenths out front, and here's what it would be. It's a 4 over 7 parentheses x minus 4. That makes this one a 3 over 7 parentheses x plus 3. Yeah, there we go. Either one of those is just fine. Now, I'll admit it, this one looks better. If it were on a test, I'm totally fine with either one of them. If you wanted to stop right there, that's okay. I'd prefer this one right here if you can, but it's not that big a deal. Any questions? Okay, what do I do first? Factor it. X plus 2. I've got an x. Let me do that over here. X squared minus 2x plus 1. Remember how to do that? What does that factor to? X minus 1, x minus 1. How should you write that?
X minus 1 squared.
You write that as x minus 1 quantity squared. Now, a second ago, Zach was asking, well, what if it does repeat? Here we run into one where it does repeat, so let's take a look. Does everybody agree that there had to be an x? Okay. Okay, now, I'm going to write 2 more fractions. One of them is going to be an x minus 1, and the other one is going to be an x minus 1 quantity squared.
Why?
Okay. Go back and look at the starter question. Do you remember that there was a problem where we had 3 fractions that had the exact same denominator as one that only had 2 fractions? So here's what we do. When we go through and we write these down with the undetermined coefficients, what's the degree of the denominator? Degree of the factor in the denominator is 1, so the degree of the numerator is 0, so it's a number. What's the degree of the factor in the denominator? 1, so the numerator is degree 0. Now, don't say anything out loud. I just want you to think about this for just a second. What is the degree of the factor? Not the whole denominator, just the factor in the denominator. 1. Look at the factor. It's a degree 1 polynomial. That factor is a linear factor. So that means the numerator is going to be degree 0, so that means it's a C. Okay? Now, why does that have to be there? Why do I have to have all three of them? Why not just this one and this one? Because I've got an x and an x minus 1 quantity squared. I've got those.
It would be wrong.
Okay, again, back to the original, that starter question. There might be one that looks like this. You can't tell by looking at the end result. When a linear factor repeats, it kind of gets swallowed up in this one that occurs twice. So there had to be one with an x minus 1 quantity squared. There could have been one with an x minus 1. If there is, we're going to find it and there's going to be a number there. What if it was like that second one where there were only two factors? Guess what b turns out to be? It would turn out to be a 0, therefore this wouldn't be there. Okay? But basically we're saving a place for all the possibilities, for all the possible parts. Yeah.
So it's kind of like trying to find the real solutions and trying to find the imaginary solutions type thing. Because like imaginary ones, not real, but
I see your point. We're leaving open the possibility. We're kind of accounting for everything that could possibly happen with this. We know that had to be there. We know this had to be there. This might be there. If it is, we want to save a place for it. There's no harm in saving a place for it. Okay? If it turns out not to be there, we'll just find that b is 0 and then we're golden. Okay? Any questions? Okay. So, from here on, same technique. Again, your mainstay technique is convenient zeros. Sparingly use the Heaviside cover-up method. Okay? It only works on the ridiculously easy ones, and you're not going to see those on the test. Okay? And then systems of equations is last. So, I'm going to take this and we're going to multiply by x and x minus 1 quantity squared. So what happens every single time over here?
It's a numerator.
It's just the top, right? Or however you want to pronounce that. Okay? Yeah.
How come we didn't times it by like x minus 1 quantity cubed? Because don't we have the x minus 1 and x minus... Oh wait, I just saw it. Never mind.
Good. Thank you very much. Appreciate you answering your own question. This is going to be x minus 1 quantity squared. This is going to be bx and x minus 1. And this is going to be c times just x. Okay? Because when you multiply, only a factor of x minus 1 cancels, so there's an x left and one of the x minus 1s.
Okay.
Everybody okay with this?
Yeah.
Okay. So when you have a repeating linear factor like this, if you want to skip straight to system of equations, that's okay with me. I kind of like using the convenient zeros. I find it a lot better that way. So if you have convenient zeros, it's probably in your best interest to plug those in. Do we have any?
Yeah.
We do. What's the first one?
0.
Okay, I'm going to go with 0 if that's okay. If I plug in a 0, I get a 2. I get a 0 minus 1 quantity squared. Okay, watch. 0, 0 minus 1, c times 0. What happens to both of these?
They go bye-bye.
So this is a 1. So this means a is equal to 2. I know what 2 is. Sorry, said the right way. I know what a is. A is 2. Okay, do I have any more convenient zeros? I have a 1, so let's plug in a 1. If I plug in a 1, now everybody watch please, this is going to turn out to be a 3. Okay, could we skip just a little bit? What happens to this if I plug in a 1? It's gone. What happens to this if I plug in a 1? That's gone. What's this? That's just a C. Okay? So I wouldn't write these slashes, I'd just write C equals 3. And I know what A is and I know what C is.
But there's no
Okay. Nope. There aren't any more convenient numbers to plug in. So this is when I'd turn to that other technique of system of equations. So I'm going to take this side, and here's what we're going to do. I'm going to write x plus 2, and then I'm going to plug in the parts that I know. I know that a is a 2, right? I don't know what b is, or if it even exists yet. And I do know that c is 3, so this is going to be 3x. With me there? Okay. Now I just multiply these out. This is x squared minus 2x plus 1, and then distribute the 2 through. So this is 2x squared minus 4x plus 2. If I distribute through here, this is going to be bx squared minus bx, and that's just a 3x. And on the other side is an x plus 2.
That looks so pretty.
Okay, now, we need to organize this. Okay, I need you to watch and listen. This is the last example, and then we're done. You can go home, let this cook for a while. Are there any x squareds over here? There aren't. So I'm going to write 0x squared, and I'm going to write plus 1x. So 0x squared plus 1x plus 2 should equal, let's go through and collect terms now.
2bx squared.
Okay, watch. This is how you should write these down. I find this much more convenient. Start a set of parentheses, write that coefficient. Then write that coefficient. There are no more x squared, so close the parentheses, slap the x squared on the end. Okay, we're done with the x squareds. Let's go through and look at x's now. If I go through and look at x's, again, watch. Eyes up here. Need you to look. Write plus, start a set of parentheses. We're going to write down the coefficient for the x term. There's a -4. The next one is a minus b. And the last one is a plus 3. Close the parentheses and then put an x on the end of it. Hold on one second. The only thing left here is what? A plus 2. Now, take a good look at this. Okay, look at those colors there. If these two polynomials are equal, shouldn't the number on this side equal the number over here? And does it? Okay. Now you look at the rest of it. Tylin, you had a question?
Yeah, I was just saying, well, if the 3 wasn't there, could we just put the negative outside the parentheses? And then make both the 4?
I wouldn't. You're much better off putting a plus starting the parentheses, even if everything inside is negative. You'll be much better off. Okay? So, take a look at these other things. If this is the x squared term over here and this is the x squared term over here, shouldn't the coefficients be equal to each other? So 0 equals 2 plus b, right? What does b equal? B equals -2. Now, we're done finding a, b, and c. So there is a b. It's a darn good thing we saved a place for it because b is -2. We're done, but I want to show you something. We're going to go back and we're going to rewrite the fraction as its parts. But watch this. I didn't use this purple thing right here, did I? Watch what happens if I do. That would say that 1 equals -4 minus b plus 3, right? That would be 1 equals, that's going to be -1 minus b. Move the 1 over, that's going to be 2 equals -b. So what does b equal? That confirms that we got it right. So there's only one number b can be, and it's got to be -2. So now we can come back up here and we can say, hey, you know what? We were going to break this into potentially 3 different parts. We saved a place for that third part if it actually is there. Okay, and now we can write 2 over x. That was -2, right? Minus 2 over x minus 1. And what was c? 3. 3 over x minus 1 quantity squared. Now, why is this the answer? Because if you took that and added them together, what would you get? You'd get that original problem, okay? Long, drawn out. We'll finish this tomorrow. Please take some time, look at those examples. It'll make tomorrow go a heck of a lot easier. If you've got your project, I need it right up here.